All right, so in this section of Unit 3, we're going to focus around potential energy. All right, and so just remember that this is also kind of that physical science definition. Right, so energy that is stored for later use is known as potential energy. Right, and if you remember from middle school science, right, that's essentially the definition that you're given. Right, and so stored, right, and so basically what really happens is any force. Okay, the majority of the forces that we talk about do have potential energies associated with them. The two big ones that we're going to look at here are going to be what is known as gravitational potential energy, potential energy, which we call U sub G. And then the second one is going to be elastic potential energy, okay, which is going to be U sub S. The reason why I call it U sub S because this is going to be the spring force, right? So, and then this will be essentially the weight, right, or the gravitational pull, right? And so one thing to know is that these are two what we call conservative forces, and all conservative forces do have potential energies associated with them. Okay? So first, let's dive into gravitational potential energy. So gravitational potential energy is the amount of work required to move it, let me say an object, right, from one location to another, okay? And so the equation is just going to be simply U sub G equals mgh, right? And so if you want to break this equation down, right, mgh, well, and we're talking about how this is a work, right? mg is F sub G, so that's a force, and H is a special distance. So notice that we're just multiplying force times distance with this equation, okay? Just like every other energy, the unit is going to be joules, okay? And at this point in time, that's all it is for gravitational potential energy. So let's take a look at a couple example problems. So here you have find the gravitational potential energy of a 65 kilogram person sitting on a diving board that is 3 meters high. And so all we're going to do is plug in our values, right? So U sub G equals mgh. So we're going to use 65, we'll use 10 for simplicity, times 3. And so you do 65 times 10 times 3, you find that the person sitting on top has 1,950 joules of energy stored, okay? We'll get into conservation energy in a little bit, and if that person now jumps off the diving board, this potential energy will be converted into kinetic energy, okay? But that's when we're going to talk about conservation of energy here very shortly, all right? The next one, a candy bar called the Mountain Bar has a nutritional energy content of 8.87 times 10 to the 5th joules. So if an 81 kilogram mountain climber eats a mountain bar, it converts all of its energy to potential energy. What altitude gain can the climber achieve? So this kind of goes back, so we wonder why we count calories. There is a joule to calorie conversion. And so this is what happens, right, when we eat food. All that energy in the food, right, all the calories, we're going to convert it to other forms of energy, okay? And so we start with our equation, U sub G equals mgh, all right? And we're going to solve this equation for H. So all we're simply going to do is just divide by mg. So U sub G equals, or H equals U sub G over mg. And so it's going to be 8.87 times 10 to the 5th joules divided by 81 times 10. Okay? And so when you do that, you're going to find that they can climb 1,095 meters, okay? Which is short of a mile. If Quest asked you to convert this to miles, you would just say 1 mile, right, 1,609 meters, which I didn't do that calculation on the sheet, but if we do that, it's going to be 1095 divided by 1609. It's about 0.68 miles, right? So just under 3/4 of a mile. Okay. All right. Now, this is not the only potential energy that we're going to account for here. Okay. The next one is the one associated with springs and rubber bands. And so we refer to this as elastic, or springs and rubber bands are referred to as elastic because they return to their original size and shape after being distorted. Now, again, this is a conservative force, right? This is the Hooke's law we talked about. Okay. So we talked about Hooke's law before. And we talked about springs, back and forces. So the potential energy stored in a distorted elastic material, right, is called elastic potential energy. Okay. Sometimes you'll see it abbreviated as U sub E. I just use U sub S because most of the situations we'll talk about will be for springs. Okay. Now, when a spring with the force constant K is stretched or compressed by a distance x, the amount of work done on the spring is equal to 1/2 kx squared. Now, this is also the spring potential energy equation. They're the same thing, right? Because when you stretch a spring, you're giving it potential energy, okay? And you're doing work on the spring. Now, the work is stored as elastic potential energy. Right? So when you stretch that spring, you're giving it this elastic potential energy, and then when you release it, then it gets converted into other forms of energy, gravitational potential energy, kinetic energy. Okay. All right. Now let's just look at a couple of equations with this. So this says that a spring with a spring constant of 120 newtons per meter is compressed a distance of 2.3 centimeters. How much potential energy is stored in the spring? So we're going to use our basic equation. So 1/2 kx squared. So we're going to do 1/2 times 120. Now you do have to be careful because this is in centimeters and our K is in meters. So you need to make sure that these are in the same unit. So we're going to do 0.023 meters, and we're going to square that. I'm just going to confirm my answer. 0.5 times 120 times 0.023 squared gives us an answer of 0.0317 joules. Okay. Now notice this spring, right, doesn't store a lot, right? But if you take like a garage door spring, right, that's going to store a lot because your K value is going to be much higher, right? And that's why garage door springs tend to are very dangerous if they ever break. Okay. Next question says it takes 20 joules of energy to compress a 1 meter spring to 70 centimeters. Okay. How much work would it take to compress the same spring from 70 to 50 centimeters? Okay. So the first thing we're going to need to do is we're going to need to figure out what is the K value of this spring. Okay. And that's going to come from using our equation. Now, this is remember this X really is a delta X, right? But again, it's not, a difference of those because the individual X is squared. So it's going to be like X squared minus X, final squared minus X initial squared. Okay. Now, what you will end up seeing is that this will be, right, I mean, it looks like it's going to be a negative number. So let's just work this out. So what is K going to be? K is going to be 2U sub S over this difference. Okay. And so when we plug this in, we're going to do. Sorry, I'm just doing something real quick.